So I'll hit go live and I'll wait to hear an echo because I need to make sure we're live on YouTube. It always takes a second as I rotate my head around the screen trying to figure things out. I'll give it a second. Awesome, I hear an echo, so that means we're live. Let me move things out of the way and quickly get to it. One moment. I need to copy a bunch of links and paste them in the chart. It's the first one. Second one. I'll just take one quick minute before making sure all of the links are there in the chart. Please ask questions in this link. So to the people already watching, I'm just making sure everything is there in place, both on YouTube and Zoom. I have shared a link to the discourse thread where we'll be taking questions from, and I've pinned the message this time so that no one gets confused. That was one of my mistakes earlier. Sorry about that. All right. I'll take off my headphones because I've realized that I don't speak loud enough. I can hear myself in my headphones. So for that reason, I don't speak loud enough because it feels like I'm speaking quite loudly, but that isn't the case. I'll stop talking about general things and get to work now. Welcome back, everyone. It's always exciting. Sundays have become so exciting now for me because we're learning PyTorch together. To all of the people joining us regularly, you know that it's a framework that I really like, quite a few people like, and as a community, we're just learning stuff together. And that brings me to the nice announcement from Weights and Biases. We've been working on all of these things together. Aman Arora, my colleague, has been hosting a very nice study group around fast AI. We've been reading papers together as a team, all of us, and we're excited to share that we'll be hosting our first community hangout next Saturday. So if you'd like to join and hang out with just the people from the community, get to know each other, you're most welcome to. We aren't going to be studying anything. Honestly, it's just a way of us getting to know each other. Let me make sure. I see a few messages, so I'm just trying to see if anyone is complaining about the audio. Doesn't look like it. Awesome. I have one request as well. It's this is a community that we're building. So if you haven't shared your journey or introduced yourself, please do so in this thread. It's linked out here. We're trying to award people with interesting backgrounds. So we'll be sending some swag their way. We'll announce this during the hangout. So people with the most interesting journey or story, will send some swag your way. We're also, this is a project where you all, especially from this study group, can contribute. So the link I have shared to the announcement has these linked off there. If you click on this, it will take you to PyTorch best practices. We're creating a wiki. By this, I mean, we're creating a collection of resources. If you'd like to contribute to this, you can simply edit this. It's a post, or you can reply with your favorite resources based on the topic of PyTorch best practices, model deploying, all those things in PyTorch. So we're trying to go beyond the book, and you're welcome to contribute. There's no obligation whatsoever. If you do, we'll be sending swag to the people who contribute as a way to encourage that. So if you like, please feel free to jump on that. Awesome. Secondly, I want to point this link out. I've already shared it across the chats. And if you head over to this, you can ask your questions here. And you can reply to the thread directly, I'll be keeping an eye out on here. I have again caught a bad fever, which means that I'll be taking a few more water breaks, or I'll be sipping a bit extra bit of water. So you all will get a lot of opportunities to ask questions. Yeah, but apart from that, I'm quite excited to again iterate through all of these things. So this is what we had studied last week. It was PyTorch tensors, autograd, and neural networks. What I'm trying to achieve through this study group as a reminder is I'm trying to recap everything from the book. So it's not about adding stuff necessarily, but it's about highlighting the things that I really like the most in all of the chapters as a way of, giving you a heads up if you're going to read the chapter later on, or as a way of recapping everything if you've read it. Again, there's no structure to it. We'll be glancing through chapter 5 to 7 today, and I'll try to weave between the theory and the code. As a reminder, all questions will be taken from this link, which should take you to our forums. Now, I want to mention one thing. Last week, I rushed a bit through the concepts, and that's because I'm trying to copy this approach. This is a slide from one of the best courses in the world called Faster.nn. I'm sure you all know of it, but it talks about explaining concepts first in code and having this bigger picture. So as I was trying to rush through different concepts in our previous meetup, I was trying to tell you about what do models mean? How do you train them? What does training a model mean? What does a neural network mean? This thing is called an optimizer. This thing is a loss function. Here's how you use it in code. Today, I'll be going through them again and reintroducing them in a bit more depth. Again, this is not how it's done in the book, but I'm just trying to follow a different approach, as I really like this top-down approach, as the creators of FastAI call it. So the idea is to give you a bigger picture first by rushing through the concepts and then going through them again. I believe that this approach has worked quite well for me. So that's what I'm trying to do here. So here's the highlight from chapter 5. And just to recap, we had also covered this last week. The idea is we start with the linear model. We take the derivatives manually at first. And this is to understand how to optimize the parameters of our model. Then we introduced autograd, and then we introduced optimizers. So let's go back to the code and try to understand this in a bit more depth. Yes, we're looking at our first model today. And let me also go back to the book because I think it covers this thing quite nicely. So inside of the chapter, and I absolutely love the humor in every single chapter. There are a few takes on, let's say, theoretical physicists. I don't want to piss anyone off, but they make joke of that. There are also quite interesting comments in the sub notes. And this is rare for a technical book from what I understand. So Kepler was really a Kagler. The authors introduce his approach of understanding how did planets go around in their orbits. So what did Kepler do? He observed planets for a really, really long time. He noted those observations down, and then he tried to visualize it. I can't understand how he did it without computers or anything, but so far, please stay with me. After that, with all of the data, he tried to fit a model to it. So he tried to fit a function that would approximate these values. And he started with the simplest model, iterated upon it, and got to an ellipse. That's how Kepler knew that planets go around in ellipses. And this is actually quite similar to how Kaglers or how data scientists or how machine learning engineers approach problems. So to summarize, you have collected data, you visualize the heck out of it, the author's words, not mine. You do a lot of EDA after collecting your data. You start with the simplest possible model. So you start with, let's say, a linear model. I know we've just learned about linear models so far, but that is the simplest possible model, at least in today's world of deep learning, especially since this book talks about deep learning so much. After that, and I'm not sure if Kepler did this or not, you keep an independent set for validation. So you take a subset of your data set, you leave it aside, and you work with the remaining. And you keep fitting different models until you get a nice thing that converges on it. All of these steps can be independently matched to what we do in data science, what we do in deep learning. So this is how the authors introduce the problem. The 3 steps are: take data, choose a model, and estimate, in in very simple words. So here's it recapped. For a mental model of the learning process, you have a model, and we've not defined what a model is. So again, we're trying to see what goes in and what comes out. We pass a few inputs through it, and it has these weights. We don't know what the weights are. We don't know what they represent, but we're trying to change them in a way that we get an output that corresponds with whatever output is expected. So let's say we're trying to predict temperatures, which is what we literally do in this chapter. We want the predicted temperature to be the closest to the value that we actually have. So if we're trying to convert from Celsius to Fahrenheit, that's a straightforward answer. But if we're creating a model to do that, we measure the error function, which means how off are we from the value that needs to be projected. And using that, we optimize the weights. So we change the weights. We haven't discussed how we do that. We just get this value and somehow magically we update the weights, and we repeat this process until we're satisfied that the outputs are actually quite realistic. So as the authors call a hot problem, that's what we look at in this chapter. And now I'll switch over to Jupyter to explain things. Again, as a reminder, thanks for pointing this out, Girijesh. Many people have asked this question. All of these notebooks are from the repository directly. So this is the course repository, and the link I had shared earlier, this has links to it. So please find the links to the repository and everything else that I'll be covering in this thread. So the authors have created these tensors, which have some values. So this is temperature in Celsius. This is temperature unknown. We're trying to predict temperature unknown. Last time I went through this, but I rushed through it. Now we're paying attention to everything closely. We define a model which takes these in, and our model is a linear model. So we're starting simple here. This is a function that defines a straight line. And as we'll visualize the data later on, our data is actually linear. So it follows a linear relationship. That's why this model works. But we're starting simple here. We define a loss function where we take the squared difference of the losses. Inside of the book, there's a plot that we had discussed last week. The reason for using squared differences is it penalizes large losses, or large loss values are quite significantly shown compared to smaller loss values. So if we're slightly off from our prediction, it's not as heavily visible when compared to larger loss values. We create weights and biases. I have absolutely enjoyed reading weights and biases in every single paragraph of these few chapters, but we create a model by first creating these parameters called weights and biases. We pass these to the model and we get the prediction. So this is the first prediction. Nothing has been trained. We have just defined these and gotten these values out. The values are like so. Now we call the loss function and we get quite a high value, which means that we're quite off in these values that we have predicted. So T_P represents the predicted value. Now I want to cover this in a bit depth because this section actually discusses broadcasting, and let me go back to the book and scroll to that page. So again, I try to cover these things independently because I introduced this concept a little while ago of broadcasting. Now I'm again trying to come back to it. I'm just trying to copy Jeremy Howard's approach of introducing concepts first and then revisiting them in greater depth. That's why I introduced this a little while ago, even though it wasn't there in the chapter. Let me grab my pen. All right. So as you can see, we're creating a bunch of tensors here, X, Y, Z, and A, and we're performing different actions on them. So what happens if you have a tensor 1, that's your matrix, and you multiply or do any form of arithmetic operation with this matrix using one simple scalar. So if you add this in the definition of mathematics, or if you show this to a mathematician, he will be quite annoyed to see this, he or she. But in PyTorch or in NumPy, this is quite easy to do. So what happens internally, we don't have to worry about this. And this is the easiest way of writing it. Why do we do this in the first place? The reason for doing that is computer scientists are quite lazy. So if I write a plus 1, that should work even if it's a matrix or if it's simply a number. So 2 plus 1 should give me 3. And if I write a plus 1 when it's the matrix like so, we should get 3, 2, 3, 3. So that is broadcasting for you. Now, whenever we have such a mismatch or we're performing an operation, the internals of PyTorch and NumPy automatically take care of it. And these are quite optimized, which means that if you write for loops, they will definitely perform worse. This is one of the reasons why we really need to use PyTorch, because it's quite fast at all of these things, or NumPy for that matter. So I would advise you all to write these down on paper. I won't run through all these 3 or 4 examples. I'll mention the last one. So here we're multiplying these 3 tensors and we're checking the shape of it. So let's see, we have a matrix Y, which is 3, 1 in size. Z is 1, 3, and we have a 2, 1, 1 matrix. So what happens first, we multiply these two, simple matrix multiplication happens. And if you've done matrix multiplication enough number of times, the output will be row by column 2. So we'll get 3, 3 as an output. And now this will be multiplied with this particular tensor. But that's not possible because the dimensions don't match, right? So what's happening right here is we have 2 batches. You can think of it like so. So we have 2 batches of 1, 1. So let's say there are just 2 numbers. I'll say they're both 1. For some reason, I triggered my Siri. Sorry. So let's say both of these numbers are 1, and we're now trying to multiply these with a 3, 3 matrix. So what will happen is we'll create 2 batches of 3 by 3 tensors. So the output we get from this will be of this size. I'll take a pause to see if this was clear for everyone. I'm sure it would be, but I'm just trying to make sure if this is the first time you're looking at broadcasting, I hope it's clear for you. Okay, I don't see any questions. So I know all of the people in the call are quite seasoned, so I apologize if I'm making sure these basic things are clear to you or not. I'm just trying to make sure the beginners have a good grasp. All right, moving on, we define the first way of updating the weights. Weights are a learned parameter, and we're trying to update those so that we can predict the right temperature. So we take the simple approach, and you can go through it and understand it. But what we're trying to do here is, if you move your weights left a little in the graph and the value goes up, or if you move it right and it comes down, just move it in whichever direction where the weight value goes down and update them like so. So you update them with the rate of change of weight. And this is how we calculate it. So inside of the book, what we're trying to do is we first do this manually. We tell you why this is a bad approach. I'm sorry, I'm saying we, but the authors. So this is from the authors. I'm just reading it out loud. I didn't have any contribution to it. We show you the simplest approach and tell you why it is in the best. Then we go towards the smarter approach. And at the end, we show you the nicest approach, which is just importing everything from PyTorch. So we incrementally build on top of these things as we understand these concepts. So going back to the concept, this is how we update our weight. And we do the same thing for the biases. We differentiate every single thing. And towards the end, we just update all of them. And this is followed by that. We talk about differentiation. I'll skip this over because it's quite mathematical and you can understand it if you want. But again, it's a better way of approximating things. The reason why we do these steps is because this particular method, it works okay if we have two parameters right now. But realistically, when you look at different models, there are quite a few number of layers, there are quite a few number of matrices. So even weights right now has a few number of parameters. If I manage to spell it correctly. So it has a single value right now, and same is for B. But as we scale this and add these to our input, it becomes a lengthier tensor. Now you can imagine for a particular neural network, there would be many layers and there would be a lot of functions. So this approach of defining it like so doesn't scale well for that. So that's why we use differentiation. That's one of the ways of doing it. I won't explain it because this is the only time we look at it in the book. You can go through the mathematical definition, but I'll skip over it. And you can update the parameters using that. When you do so for the first time, you get to a loss of infinity. So what we were trying to do here is we were trying to minimize the loss. But as you see, it increases with every single epoch and it just goes out of control. So what do? We do the most obvious thing that every deep learning practitioner would do. We would just start by changing the learning rate. So the model definition is right. That's what we assume. And we simply change the learning rate. As a good rule of thumb, it's always nicer to divide or multiply it by factors of 10. Since the gradients exploded, so this is known as gradient explosion, we would divide them. So in our case, we divide them by 100, which is why we get to this value. And this time, a loss values come down to a nice value of 29. And again, this value means nothing. So if you've seen or if you're asking yourself, why is it not 100%? Why is it not a 99%? That doesn't matter here. We're just trying to minimize the value right now. I'm just scrolling to see if there's anything else that needs to be covered here, but I believe I got the crux of it. So we revisited the model and we managed to predict this straight line that fits like so to our data. If we were to use a neural network, you could imagine it could be a zigzag-like line if we overfit. But I would say this is quite moderately fit. And right now we can't do anything else because by definition, our model is going to be a straight line. And we managed to get it quite close to our data points. So let me quickly take a peek at the questions. No questions so far. All right, I'll continue. So now we get our first introduction to autograd. The most exciting thing that happened in machine learning in 2015 was we got introduced to TensorFlow, and TensorFlow had this concept of creating static graphs. The best thing that happened afterwards, in a way, we got introduced to dynamic graphs. So when I say static graphs, let me show that with a quick illustration. What do I mean by that? As I stop sharing and start sharing again. I'm sorry, this always takes a minute, and that's because I could leave everything open, but then it's not the most optimized size for YouTube, even though it works well for me. So static graphs have this defined way of having, let's say, input 1, input 2, you do something with it, you pass them to a particular layer where, let's say, you just add them, followed by which you have an activation function. We covered activation function last week. We look at them in depth, and you get an output. So originally, TensorFlow forced us to define all of this first of all. So it was a static graph. But the nice thing that happened later on, and now it's common to both PyTorch and TensorFlow, Both of them allow you to have a dynamic graph, which means that you can define anything and you don't need to know the exact sizes of tensors that go in and come out. You don't need to know exact values every single time. And PyTorch accounts for it, or TensorFlow Keras account for all of the options. And these get computed in runtime. So what does autograd do here? I'm sorry, let me quick Slack in a second. I was getting a few notifications. Autograd, whatever we did here manually in code right before this, we computed the gradient. We try to estimate how do we arrive at smaller loss values. Autograd does this magically, automatically for us. We don't need to worry about anything. So what do we do in practice? We define a tensor called x, and we simply pass one argument, which is requires grad equals true. So here it's false, but you ideally want to have it as true. And now anything that involves x will be kept track of. And if we do a loss dot backward, so we do a bunch of operations on x, and towards the end you get a loss value from it. The loss value involves certain operations on x, right? So when you do loss dot backward, it performs all of these derivative functions for you, which you don't need to understand. What's going on here in a summary, we get the gradient of loss and we get the value by which we should be updating it. So in essence, that is called the backward pass when we are training models. Right now, it's not a neural network, so I didn't say it's a backward pass for neural networks, but it's the backward pass for any model. So looking at this in code, we again define the same functions. We define the unknown value like so. We define this exact same model, exact same loss function. And this time, we create parameters. And parameters require grad equals true. Sorry. So we're constructing a tensor, and I'm again reminding you how to look at the docstring. You press Shift Tab twice, and somewhere here it will tell you what does passing require grad equals to true do. So if autograd should record operations on the return tensor. By default, it's false. This time we tell PyTorch, please PyTorch keep a track of all of the operations that happen on our parameters, because later on we'll compute a loss function using that. So this time, and this is known as argument unpacking. If you pass a list in Python and you put a star against it, it gets unpacked automatically. So you don't need to do anything else to account for it. Or if you have a bunch of arguments that you are going to pass to a model and you don't know the exact number, you put a star against them, you're good. You don't need to worry about anything. So this was the author's subtle way of reminding us of that. Someone's asking if they can set the values. So yes, for the first values of the parameters, specifically for this lecture, we define the values. Usually we instantiate them randomly or using a certain method. We'll learn about those later. Ideally, you need some values here. They could be random. They could be pre-trained weights. So if they were pre-trained, someone would have figured these values out and we'd start from there. So for now, we define them manually. And our loss involves the parameters. So that's the thing to note here. Now, this involves the autograd function. So whenever we call loss.backward, the gradients for parameters get calculated and we get them in params.grad. Now, I want to point something out here. We're accumulating these. We're not just storing them. So if you don't set these to 0, that's always one of the most common mistakes for any practitioner using PyTorch. We forget to set them to 0 and we always end up accumulating the gradients. So gradients get accumulated by default and you want to make sure that they're set to 0. So what we've learned so far, if we set requires grad equals true, that'll allow us to calculate the gradient, which will allow us to update our parameters or weights. Here they refer to the same thing. And what we're doing in the bigger picture, we're iteratively adding things. So we just learned how to add autograd to the function we had just built. So we look at the training loop again, and this time we calculate the loss. Sorry. We calculate the gradients and we update them like so, as we did earlier. But this time we're doing a caveat. I'd like to mention this caveat here. We use this context manager here because again, the authors will introduce a nicer way of making this go away. So when we are updating the parameters for that particular operation, and the reason for this is when we are updating the parameters, we don't want this to be accounted by autograd. So whenever we create any function, any damn function at all from a tensor that keeps track of the gradients, PyTorch will add it to the gradient calculation method. We don't want that to happen when we are updating it. So we tell PyTorch here, please don't calculate the gradient for this particular step because we're literally updating them here. That's what we do, and we return them. So that's our training loop. Now we pass the same values to it. And if I remember correctly, you can verify these values are quite similar to what we did earlier. They might not be the exact same values because there's some randomness to it, or they might fluctuate a bit. But this is to showcase we've reduced our number of lines of code. We made it simpler for us. Our life as a developer is better, and we can simply use loss.backward to calculate gradients. Let me take a pause for any questions. Vinayak, you're right, but I think what Ritubrata, I think this is Ritubrata, right? Always great to see you, Ritubrata. We were talking about argument unpacking here. I believe that's what he was referring to. All right, I'll continue further. I'm sorry, I'm seeing the Zoom chat pop up, but please could you ask these questions here because it's quite difficult to monitor all of these things in parallel. As you can see, it takes me a second to switch windows as well from the code to the book. So I'd appreciate it if you could ask the questions there. Okay, now coming back to our way of getting rid of code and making things easier for us as developers, let me now go back to sharing the book again. Now we look at optimizers. The name gives it away. Optimizers help us optimize different values. In our case, we're trying to optimize the loss value, so they help us take care of that. And once I find them, I'll tell you what they do by using the image the authors have created. So this is the conceptual representation of optimizers. So we have the model, we have the parameters, and the optimizer also keeps a track of the parameters. And they hold a reference of it. After the loss is computed using the input, we call backwards. And this leads to being the gradients being calculated in the optimizer. And now the optimizer can send these when we want to update them. So we call the optimizer now instead of simply doing it ourselves. And the optimizer updates the weights accordingly. I think I should switch back to the notebook for this part. But for the first bit, we use stochastic gradient descent, also known as SGD. As expected, it's simply a module called optim. Now, whenever you do dir in Python, it just lists every single thing in this. So what we've done here, or what the authors have done here, I'm sorry, it's not me, it's the authors who are doing these. We list every single optimizer function in PyTorch. And as you can see, there are a few. You can also define more if you need. And there are a few that aren't here, not the most common ones. This is one of the homeworks I have for you. And this time I've noted down the homework for everyone because we're at the point where we can do a few experiments. We'll be looking at SGD and Adam in this particular code example. I would encourage you all to at least try the other options. So in our approach of getting rid of as much of code possible as we can, this time we define the parameters as we did earlier. We define a learning rate. It's slightly different this time. We define an optimizer and it's stochastic gradient descent. Let's see what does it tell us. It implements stochastic gradient descent optionally with momentum. What is that? You don't need to know right now. If you want to know, don't look at the theory. Try passing momentum as a value. See what does that do. Theory is an interesting loop. I always try to mention this. Please don't look at as much theory. Try to look at twice as much code as you look at theory. So try all of these different values, not just for SGD, but also for different optimizers. We pass the parameters and we pass the learning rate because that is what our optimizer expects here. Everything else has the default parameters. So these are the two things we absolutely need to pass to our optimizer. And now our training loop has become just a few lines of code. So this time we set the optimizer to 0 grad. We don't want our gradients to accumulate, sorry. We call loss dot backward. So we calculate the gradients and we call a step on the optimizer. So this performs a single optimization step, which means this updates our gradients. That's all. So as you can see, we again get to a similar value as earlier. And when we try the same thing with Adam, the same value comes out of it. The authors were trying to show that these are slightly different because Adam is quite less sensitive to values not being normalized. Again, the point made by authors, and I want to highlight this as well. Why do we normalize things when we send them into models? That's because as we are updating all of these different millions, possibly sometimes even billions, if you're a large organization, billions of parameters, you would want them to be updated on a similar scale. So let's say if some value is on the scale of tens of thousands and some value is in decimals, and you update all of these, it's not going to reflect as nicely. And it's quite difficult to keep track of that. So that's why we normalize all of our values before passing them into a model. I'm not sure where this was covered in the code exactly, but I wanted to highlight that. Now we go back to the Kepler's way, and Kepler had set aside a validation set. He didn't call it validation set, but for the sake of deep learning, we'll call it like so. So what do? We take a small subset of our data, it being 20%, and we called torch.randperm. What does that do? Let's see. I have forgotten as well. It returns a random permutation of integers from 0 to n minus 1. So we get a bunch of shuffled indices. We get a bunch of random indices, and we create a validation set out of it. And we set these aside. We don't look at it for the longest time possible. And we'll use our model to check if we're performing nicely on these values. Only once we've, sorry, I was mixing the two concepts. We keep looking at this, but we don't train our model on this. Sometimes we also have a test set, which we only look at after we are done training the model. So this time, all we do, we account for the validation loss, and we don't call backwards on it. We're good. We don't need to do that. We're just accounting for it. I believe later the authors showcase how can you also account for validation loss updates. Usually that never happens in practice. Okay, I think that marks the end of chapter 5. I'll again take a pause for any questions. The question asks, how much do you balance both of these? So I started my journey with Fast AI. I read the Fast book before this. Honestly, the reason I'm also running the study group at Weights and Biases broadly, we want to encourage everyone to learn. I think this complements Fast book quite nicely. So to the people who've gone through that course, and I recognize names who have been writing incredible blog posts for those study groups. I think what, and I'm speaking on their behalf, this covers and complements things from a very easy standpoint. We start with small concepts, we build on top of them. So it's again an alternate perspective that you get from the study group. If you have the time, we'd encourage you to check both out, but it's totally up to you. All of these are just for your learning. We don't have any other agenda for it. I'll speak about papers and I'll talk about them with a grain of salt. At one point in my career, I was told to look at deep learning papers. Let me stop sharing my screen so that I can emphasize on this. I feel like when I stop sharing the screen, I can emphasize on things and it feels like I'm emphasizing on a topic. At one point in my career, I wanted to really read papers because that concept had come up so many times. People had told me, hey, Sayyam, if you want to be a good deep learning practitioner or researcher, you need to read a lot of archive papers. That's true. That's absolutely true. But for me, the challenge was I need to read as many papers as I can. That's one pitfall that I fell into and I see people falling into. So please don't just read papers. Try to go through their code as well. At least for me, most of my intuition bottleneck lies in code and not in mathematical concepts. So do read papers if you like, but remember to try things in code. Remember to look at the code of the papers, and with time you'll get to a stage where you look at a certain definition inside of the paper, and you can automatically correlate it in a way, at least, to code. That's what you need to aim for. That's why you need to read papers, because researchers represent ideas in a certain way in research papers. But what really works and how is that done? That's done using PyTorch code or Keras code. So please build an intuition there and not just focus on reading papers. Uh, I'm sure you wouldn't be doing that but also try to not just read through code. When you get to the stage of just reading code, also try to replicate it yourself without looking at the implementation by the authors or any alternate one, since you mentioned papers with code. Papers with code has many repos in TensorFlow. How to deal with that? Deep Learner 007, you can be the bridge. So Prabhav, you can be the bridge for us. You can port them over to PyTorch. And that is not a light task. That becomes an intensive task. So intense that you can mention that on your resume. And I know incredible companies that can that give value to that. I'm sorry, Ritubrata mentioned this isn't a wiki. Let me fix that. Sorry, this wasn't a wiki. I forgot to make the top post a wiki. Thanks for pointing that out. How do I recommend tackling PyTorch and FastAI? Um, FastAI is a superset of PyTorch. So you can take either things at the same time. If you're taking both of them alternatively, there'll be overlaps and different things will be covered. So you need to account for that. So please be careful and mindful of that. I'll come back to this question. So the question asks, they can't load a particular data set. Now you'll have to build a data set class for it. How do you do that? We'll just look at that later on. Thanks for pointing this out. There's also a development test set. Although in practice, I've at least for Kaggle, I've not seen a fourth data set being set aside. I can't remember. I haven't changed anything to account for it. All I do is I press Shift Tab twice. And that brings up the doc string. If you can't do that, you can write 2 question marks, and that should bring things up for you. So that should tell you that, and essentially here it'll just bring up the source code. Older papers are in TensorFlow or Caffe. So for people that don't know Caffe, let's see if I look this up, what does it that bring? Okay, maybe Google knows that I keep looking at deep learning a lot, so it optimizes. I'm not sure if this would come up every single time, but it used to be a deep learning framework, and I'm assuming a few classical. It hasn't been updated since 4 years as well. But a few classical papers might be written in this. How do you account for that? Try to port them over in PyTorch. As you go through the book, right now we're still on the early concepts, so we're still learning about how this autograd work, how do optimizers work. But I'm guessing right after the second meetup, so the meetup that happens after this, we'll start building a project. At the same time, start trying to port models from Caffe to PyTorch. And please feel free to start a thread on the forums. I'd be happy to help you there. I'm sure other people would join as well. This would be quite an interesting project. Okay, I'd be happy to cover setting things up. Maybe I'll do that separately in a thread. Thanks for that request. I'll continue with the chapter now. Ritubrata can't reply more than a few times. I will grant him a higher status in our system. Okay, Ritubrata, please don't burn anything. Now you have, I think, moderator status. Please be careful. But you should be able to reply to the thread. Thanks for pointing that out. So let's see. Now I'll go back to sharing the book, or yes, let's start with the book. I'll mention that first. I'm sorry I went on this tangent of, really it was a rant of talking about papers, but I really feel I've hosted a few study groups in my journey. That's part of my career journey, and that's one pitfall that people fall into. So sorry about that rant in a way. I really feel it should be quite emphasized upon. So last week we looked at overfitting and underfitting. I won't go through it again. I believe that covered the crux of it. As the authors called it, we have looked at the appetizers, and with this chapter 6, the main course begins, which is neural networks, which is what we're here to learn about. And as a reminder, this is the learning process. We just spoke about it, so I won't talk about it. But here, the weights or the model is a neural network. So this time, this particular key thing is a neural network. And this is how they're represented mathematically. So it's a bunch of linear transformations or a linear functions, bunch of linear functions followed by a non-linear function. The reason for doing that, or the reason for adding this non-linearity, it's quite hard to estimate. Now, this is again a hand-wavy claim, and I won't show it in mathematical proof, but please believe me when I tell you this, it's quite hard to estimate complex surfaces. What are complex surfaces? Surfaces of higher dimension using just linear functions. And if you add enough linear transformation and non-linear functions, that allows you to be able to calculate anything. That is known as universal approximation theorem. Again, that's just a theorem. In practice, what this tells you, neural networks work quite well. And how do they work? They are based on a bunch of linear transformations followed by non-linear functions. That's not the best explanation. And I'm skipping over the mathematical details again, because if you'd like, you can dive into them. I'm just glancing over them. So what is a multi-layered neural network? we have a bunch of layers in it. Every layer has a bunch of neurons. And this is how it looks in code again. So this is the first layer, or it could be input. Some people count this as a layer, some people don't. Don't at me. Let's just call this a layer. So we input our values, we pass it through nonlinearity called tan h. What is that? We'll quickly learn about it. After that, we again pass this particular value to the weights of the second layer. So we multiply these two. We add biases to it. And then we again pass this through a tan h activation function. And we do this a bunch of times, which gives us the output. So this particular representation or this particular approach, these represent the same thing, the exact same thing. And this is a neural network. This is the thing that has created all of this craze. These are the things that have shown us that we can approximate almost anything given enough data and enough electricity for GPUs. Now let's try to look at it, how to encode. Or before that, maybe I should just cover activation functions real quick. So why do we need activation functions? To recap, you need to add nonlinearity. I just explained this. And you need to concentrate outputs to a certain value. So this happens when you're trying to predict, let's say, stock market data. Now, if a stock is trading between $10 to $20, you can't predict the value 100. So even if your weights come to a value of 100 or they reach a value of, let's say they are normalized, so they would be between 0 and 1 or -1 and 1. That cannot be output because the output is supposed to be between 10 and 20. So we need to concentrate values, them to a certain value for regression problem, or if you're trying to predict hot dogs or not hot dogs, we need a probability. So we need to concentrate values. I've stolen this image from cifix.com to credit. Their blog is titled Dance Moves of Deep Learning Activation Function. I'd actually taken a printout of this at some point. But there are all of these different activation functions that exist. You can see their mathematical definition, and you can see the dance that follows. This is one way of remembering it. But the most common one is ReLU, shown here, sigmoid. And for starters, we'll start with tan h as well. So tan h follows a curve like so. Maybe I should just go back to the book because that has the nice plots. So around values, x is the input. So around the value -1 to 1, we get a nice reasonable value. But as soon as we go beyond that, the value reaches an unreasonable number. This can be taken care of using hard tan h, which fixes the value at a particular number. This is how tan h is defined. Sigmoid follows a graph like so. So as a homework, please go through these, plot different x values and see where do they correspond. And we'll quickly look at how can you invoke activation functions and get different values out of it. What is ReLU? ReLU does this simple thing. For any negative value, it gives a value 0. And for any value greater than 0, it returns a number like the input. So whatever be the input, it's returned as it is. This simple concept of, let me actually quickly write it in code here as well. So if you were to define this, let's say you would define a function ReLU. If x is less than 0, you return 0. And if x is, actually this should be less than equal to 0. And if it's more than 0, sorry, you just return x. So these 4 lines of code are one of the easiest and best way to train models. This particular activation function, when introduced, showed us how to do wonders with training models. So this is an activation function. Why do we need them in the first place? Again, we need to introduce non-linearities into our model because that is required to train for complex surfaces. There are different bunch of activation functions possible. There are a few requirements with these. They should be differentiable. Ideally, they should have a nice response between certain ranges and a not so nice response, or they should reach a state of saturation or give the same values beyond a particular activation point. I think that should start to make sense now. So they get activated in a certain range. So let's look at tan H. Let me change the color. It should get activated in this particular range of numbers. I've butchered the graph, so I'll maybe look at ReLU now. So ReLU gets activated in the positive number range, right? And before that, it doesn't get activated. So activation functions have a state of activation, which is defined differently for all of them. And they only get triggered, they only get activated after a particular value. That's where the definition comes from. So looking at the problem statement in this chapter, we're trying to predict between grizzly bear, good doggo, and a garbage truck. And the authors talk about this plot. And they plot this on tan H, and they tell us about the sensitive region and the undersaturated and oversaturated regions. So anything that's a doggo is quite much a doggo. You get that value. A grizzly bear comes somewhere in between. So let's say with lesser probability, we say it's a grizzly bear. And a garbage truck is definitely not a dog by any stretch. So it's undersaturatedly not a dog. That's how tan H does these predictions. Let me see if there's anything else that I should highlight. No, let me switch back to my presentation now. So to recap, selecting the right activation function needs you to have a non-linear activation function. It should allow approximating more complex function. How? We're not looking at that. That's mathematical. But no, for now, when you add non-linearities, that allows you to approximate complex functions. As I watch these recordings, I always realize my throat runs dry midway, and I'm trying to be more accountable for that. So the second point is they should be differentiable. The main reason being, hey, they should work with autograd. We just spent a ton of time learning about autograd. I can't go back to writing lengthier code. They should work with autograd. So they should be differentiable and they should have the sensitive range. Thanks for sharing these resources. I'll quickly cover how do you account for different activation functions while applying. And Ritubrita, please feel free to add these to the topic key if you want. So now we start looking at neural networks in code. I believe we first define them manually. No, we start by importing torch torch.nn, which is where neural networks reside. Let's head over to PyTorch docs and see what all do they contain. The reason I spend so much time jumping into documentation, I want to encourage that as a behavior. So please spend more time here instead of someone just asked how should they learn about activation functions. I just hopped into torch.nn and now I can see nonlinear activations. So go through these and understand this. But as you can see, torch.nn has all of these modules. So there are convolution layers. Don't worry about them if you don't know about them. We'll learn them, learn more about them in the next meetup. There are transformer layers that might seem familiar to you if you're in deep learning. These have taken over the world recently. Let's look at utilities as well. So this clips gradient norm of an iterable parameters. Interesting. Let's see if I can find any other interesting function. Weight underscore norm. So this applies weight normalization to a parameter in the given module. Let's keep scrolling and see if we can find more things. No, I can't point anything out. So let's look at weight underscore norm. The nice thing about the docs, it can take you to the source code. It also gives you the thing in mathematical definition, but it also talks about it in code. So as you try all of these different things, try incorporating them in your code and see what do they change. So I can't imagine where would you want to use this right now. But please spend some time going through torch.nn and try to understand different things. Try finding interesting options. Recently, I just 5 minutes ago, I pointed you to trying different optimization functions. Play around with those. Look at the documentation. Please spend some time there and try different things. So that's how you play around with these things. I hope that answers your question. That is a great suggestion. You could definitely do that. Okay, so now we are trying to create a linear neural network. Neural networks by definition aren't supposed to be linear. But this is how we're starting. We first call nn.linear. What is that? As a reminder, I press shift tab twice. It applies a linear transformation to the incoming data. So y is equal to x times a tensor plus p. So again, it's the exact same mathematical function that we apply here. And this time we can simply print the weights of the model because it's from torch.nn. We can print the bias out. And we can pass x to a linear model. What I'm trying to do here side by side in parallel is I'm going through all of these things and trying to understand simultaneously how much should I explain. So we create a linear model, we pass these two values to it, and now we do the exact same thing as earlier. We call an optimizer, stochastic gradient descent. We don't do anything, we don't change any parameters. And deep learner 007, this is what you should be doing. So try changing the momentum here. That is how you play around with things in code. Try changing dampening. It might just mess things up, but that's a nice way to play around. So you pass the model parameters, this time literally by calling dot parameters on the model, and then you share the learning rate. So what are model parameters? It's a generator, which means if we list all of them, it should generate all of the parameters. Right now, it's just two, as we looked at it earlier. This is the exact same example that we are looking at. So it's just two parameters, W and B. Now we call our training loop, which I don't think changes here. So what we've achieved here is we've created a model using torch.nn. It's a linear model right now. And now we're able to pass parameters through it directly to the optimizer. And the rest of the things stay the same. The value is quite similar as expected. It's the exact same problem. But this time, instead of manually calculating the loss, now remember, as a programmer, your job is to not write code, I just said something contradictory. So your job is to not write more code, but it's to write optimized and shorter code that can be reused. So that's what the PyTorch creators have done for us. They have written every single possible function that we usually need as deep learning practitioners. So as you might expect, the loss function we were looking at, which is called mean squared error loss, or L2 norm as well, if you're a mathematician, is one of the most common ones. Jupyter won't render these notations. You can look at them inside of the documentation. But instead of defining the loss function this time, we just called nn.msc loss. And that should give you the loss function. So now we get to the real stuff, which is adding a nonlinearity. Now, this is very much overkill, because if you remember the plot, we were just trying to approximate a linear function. That worked well. But for the sake of proving the point, the authors do this, and they do an overkill step of adding a tanh layer. So we create a sequential model, a sequential container. That's what nn.sequential is. It's not rendering properly. Let me do it again. So it's a sequential container. Modules would be added to it in the order they are passed in the constructor. So whenever we pass values to a module, we are calling the constructor. So these values are going to the constructor, which means when we call sequential constructor, we pass a linear layer to it, we pass tanh to it, and we pass another linear layer, which will be our output layer. Now we get a forward function and a similar way of calling a backward function. So we can look at all of the parameters. They are named by default for us. You can also look at something known as an ordered dictionary. So when you create a sequential model, you can pass an ordered dictionary to it, where you define these names yourself. So this is known as a hidden layer. This is known as an hidden activation, and this is known as an output layer. It's hidden because it's not visible to the output layer and the input layer. That's why it's called the hidden layer. So anything between the input and output layer, all of these things that you see in the diagrams of neural networks, those circles that you see are accounted as hidden layers. So we can also pass an ordered dictionary. This is another way of creating a nn.sequential model. And we can again look at the shape, the names, the biases. And when we call the optimizer function, this time we can, as expected, just pass the parameters like so. So this returns an iterator over the model parameters. And this is typically passed to an optimizer. So this is why you should always look at the documentation if in doubt. And when not in doubt as well, you should look at the documentation all the times, because it points you in the right direction. So this time we get a slightly smaller loss value on our training loss, and the validation loss is slightly higher. We're doing a bit of overkill, but as you can see, what's happened here, we've overfit to our training data. So we fit just to this particular problem. And what we were trying to predict here was a Fahrenheit to Celsius conversion, which should be linear. And since we've gone overkill, we've just fit to this particular example data set. So in reality, if you pass a new value to it, it might not work best outside of this range of input values. That's the harm of overfitting, just to remind you. I think these are the exercises. So I'll skip over this part and let me take a glance to see if there are any questions. I 100% second this. Thanks for reminding us all, Adil. This is true as well. Thank you, Ritubrata. All of you are sharing all of these interesting nuggets. So people are here with a bit of experience, and thank you for sharing your wisdom as well. So now we look at different activation functions. And let me remind myself what is happening in this. Jupyter Notebook. Okay, we are just plotting the different activation functions. I believe we've already covered this, so I won't go into more depth. The authors tell us about how these shapes change as we operate on different values that are going through nonlinearities. You can read about it. That's what this module shows. So I'll skip over it. One moment. Sorry, guys. As I mentioned, I have come down with a fever, but this time I wanted to prepare myself. So I'm just drinking more water to make sure I don't get in worse shape. Continuing further on, we're on this quest of continually learn about different PyTorch functions and complicate our models, which is a nice thing. We want to learn about more complicated models sequentially. So far we've done everything manually. We learned how to calculate gradients manually. Then we looked at optimizers. We looked at autograd. Now we imported torch.nn, which made our life very much simpler. And now we are going to define, I believe, our first neural network in this particular code example. So as earlier, we called the same ordered dictionary. And this time, I think this is more of a reminder to showcase you how you can create a neural network. So for this particular example, we create an input layer that just takes one value. That goes to 11 hidden neurons. Let me actually draw this. Okay, so this is what's happening in code. We have one single input that goes to this layer that has 11 different values. So let's say these are 11. Believe me on that. Don't count it. After which you pass it to tanh. So it goes through non-linearity. And since we're out of space, I'll move over here. This gives us 11 values. So tanh doesn't do anything. It just changes these values as a function. We get 11 values. And now we somehow, or at least mathematically, convert them into a single output. We may or may not have a non-linearity here. Usually we do, it's to predict these as probabilities, but for this case, we do not. So hopping back over to code. As you can see, I'm getting a little better at switching tabs. Hopefully you all won't get annoyed a bit further. I'm getting a hang of it. So now we learn how to subclass into an n-dot module. So whenever we want to create a neural network, we want to follow these particular steps. We create a subclass model from an n-dot module. We call the super constructor. So we call the constructor of this particular class. This is a Python concept, nothing new for PyTorch. So I'll skip over it. And then we define the init function or the subclass model like so. So it's the input layer. It's a simple linear layer followed by which we have a tanh non-linearity or activation, which gets outputted like so through a linear layer. We need to define the forward and backward functions. So forward function just defines the forward pass for us. It's like so. And now we create a model and print it out. It is as expected, a model with the following layers. So this is how you subclass into an n-dot module, and this is how you can create models. This is how you should create neural network models by using the n-dot module function. I think that wraps up chapter 6. Let me see if I have any highlights from there. No, I do not. So I'll mention chapter 7 highlights, and I'll again, the approach I'm trying to follow here, I just glance over all of the highlights just to give you a heads up. And in the next meetup, I go into details. This is how Jeremy Howard, my biggest inspiration, taught it. I'm trying to follow that approach, which means things will be rushed, but they'll be covered in depth later. So chapter 7 highlights the CIFAR 10 dataset. We take our first look at this particular dataset. We learn what is a torch dataset. We look at transforms, and we understand a new set of optimizer and loss functions. So going over or going back to code, CIFAR 10 has all of these 10 classes. So let me talk about the code, the data set a bit. We're trying to predict images now, but we'll be using a simple fully connected neural network. What is a fully connected neural network? We'll just learn that. But it has all of these classes. So there are 10 sets of possible classes. The images can be an airplane, an automobile, a bird, cat, deer, dog, frog, horse, ship, truck. That is why it's CIFAR 10. You can head over to their website to find more. If you simply look up CIFAR 10, it should take you to the CS.Toronto website. That's because Geoffrey Hinton is at the University of Toronto. And you can find more details of this. This is one of the most famous data sets in deep learning. So that is why we're looking at this data set. Downloading it or getting access to it or getting access to any data set for that matter is pretty much half of the job for creating any form of models. So this time we rely on Torch Visions and we import data sets from Torch Vision. So Torch Vision, as the name gives away, is the sister or brother library of Torch that is focused on vision problems. So since we're predicting images, we import that. And from that, we import data sets. And inside of data sets, we have this nice class CIFAR 10. Let's look at it. It takes us to the website, so that's good. And it tells us how or where can we download it. If it is the training data set, if we need to call a bunch of transformations on it. And what do the transforms do? A function or transform that takes in a PIL image and returns a transform version. So let's say if we do a random crop, a function takes in the target and transforms it like so. So we can do all of the different transformations that we looked at in our first meetup. I glanced over them. Now we're looking at them in more detail and we'll learn about them in just a bit. So CIFAR 10 has 50,000 examples. And the authors show you how to look at a particular image. They just grab a random image and that happens to be a red car. And these are all of the possible transforms that you can apply to the data set. Since CIFAR 10 returns us a nice object and it exists inside of data sets, we can simply pass all of these right here. So to remind you, one of the possible transformations is we can transform something to a tensor. So what we're looking at here is an image. Since it's a PIL image, that's why we can simply pass it like so. So this is a PIL image. This is not something that neural networks can work on. Neural networks work in PyTorch, work on PyTorch tensors. So we need to convert it to a tensor. So toTensor converts a PIL image to NumPy array or NumPy array to tensor. Awesome, that's just what we need. This time we pass a transform which tells PyTorch, please PyTorch convert this into a tensor so that we might be able to create a neural network on top of it. This is the shape. And PyTorch, if you remember from our first meetup, expects the channels to be first, which is why when we plot this, Matplotlib expects them in a different order, so we need to rearrange this. The authors point this out because you need to be mindful of these steps. So whenever you're working with models, these are the obvious things that you miss. Torch expects the first dimension to be channels. Matplotlib does not. So that's how we look at it. We can stack these together and create a nice batch out of it. And here the authors talk about how can you normalize them and how do you find these values. They teach us how do you find those values and how do you pass them as a transform. So now we are again adding all of these blocks on top of each other. We just learned how to pass normalizing values. We calculated them above. This is what happens when my throat dries up, start to fumble a bit. So we calculated these values and now we send these over to the data set inside of the transform list. We compose a bunch of transforms and we pass these normalization values. Why do we do this? We've learned about this. The neural network works better when values are between a certain range. So we normalize them. And that helps train models better. That is my claim. I won't prove it, but for now, please believe me, that is the case. And when you do this, remember that your image will now be distorted. So the beautiful red car that we saw a little while ago with, I think these are trees, a bunch of passengers in it. This is quite a small image, so we can't look at it. Is now with a black background and looks quite funny. That is because we have changed the values. So when we pass normalize, it does a bunch of changes to this particular tensor and adjusts its value. So that literally changes the image, because an image is nothing but a matrix having different values inside of it. After this, the authors create this task for us where they just separate out a few, actually just two classes, which is airplane or bird. It's quite funny in the book chapter. The authors have quite funny way of storytelling. I really enjoy it. I don't know about you all, but they tell us that, hey, we're a detective sitting close to airport and we're trying to predict birds using a camera. And so what they do is they just subset into these two classes. So we just grab these two particular classes from CIFAR 10, and we are now trying to create a neural network that just works on these two classes and can just predict these two. So this time we again call torch.nn and we define the number of outputs as 2 to begin with. And what do we do here? Let me share my book again so that I may talk about this. So remember, each image has 3 channels. Why? Because it's RGB and it's by 32 by 32. When you multiply all of these and you stack them together, you get the number 3072, if I remember correctly. That's how we arrive at this number. So the authors say just jumble all of this stuff together, put it into this particular tensor and store it like so. Let's pass that through the neural network. So this is our input layer. So our input layer has a tensor of 3072 and followed by that we have a hidden layer with size 512. So this goes to 512 hidden neurons. Followed by that we have a tanh, which gives us again the same 512 values changed, and we get an output from this. Sharing the right screen back again. So this is what's happening inside of this sequential neural net model. And we define softmax at first. It's of course available as a function, but we first define it manually. What does softmax do? Please look at the plot. It'll tell you about it. And the reason we call it is we're trying to predict probabilities, or we're trying to predict values as probabilities and we want them to be added to 1. How does that work? Why does that work? That is mathematical. But if you add all of these values, it gives you 1. So if you pass a bunch of values to softmax, it returns 1. Why is this important? When you have a bunch of classes and your neural network doesn't simply say, oh, this is a monitor. Oh, this is Ritubrata. Oh, this is deep learner 007. It says, this question is from maybe Sayam because it's a stupid question. This is smart answer. Could be Ritubrata. You can't say with 100% probability. Sometimes you can, but you might be overfitted. So the neural network usually would predict a bunch of probabilities. And what we're trying to predict from this is, or we take the output as the highest possible value. So the highest probability from this output is the most probable class. So we say that, the neural network thinks it's a hot dog. So we just output that. Even though there's a 20% chance it could not be a hot dog, but we'll take a chance. It's 66% confident that this could be a hot dog. So we just output that. You could call softmax through nn.softmax. It's defined like so. Why do we pass a dimension? It's optional. It applies softmax to an n-dimensional input tensor, rescaling them to lie in the range of 0 to 1 and sum to 1. And when we pass the dimension, it only applies it to the past dimension. So when we are passing batches, remember a batch could be batch by channel, by height, by width. We want the softmax to be applied to one particular dimension. When we need that to be the case, we just specify it like so. So this time we add another code block to our sequential model, which is softmax. And this is the image that we get out of it. To get the probability, we take the maximum probable output from here and look at the index of it. So here it's the index 1, which means it could be a bird. I can't tell, but this quite looks like a bird. So we're right here, even though we didn't train the model. So this is purely by chance. Let's see. After this, we define mean squared error loss. I'm just glancing over these details because I know we're at the top of the hour. So after this, the authors introduce another way of calculating loss and a few ways of doing that. So that is what they introduce in the following parts. And they again complete the module and we get to training the model with NLL loss. What is that? Let's press shift tab twice and look at it. Negative log likelihood loss. That is again one of the way of working with categorical data. And followed by that, they introduce data loaders as well. I think this is a nice point to end the session because this is an independent concept. So I'll head back to the questions and answer them. This is a great question, Sophia, and I'll start by covering this in our next session. So this will take me a few minutes. But Adil has already answered it. I should always read this first before pointing stuff out. So what I'll do is I'll read out the homework since I couldn't do that. Following are your homework items. Please check out different loss functions in Torch. Try new activation functions in the code functions that exist already. Download the GitHub repository, change out the activation function, work with them. Play around with neural network hyperparameters. So when we define 512 as a number, change that to 1024, change that to 3046, something like that. Go crazy with it. Change this code and work with a new data set. So instead of CFAR 10, try CFAR 100, try something new, try something crazy. Try a bunch of torch vision transforms, play around with the code. So this is your homework. Let me post it here. And this is again suggested homework because I'm not going to enforce it on you. But I think this is a good point to wrap up. I'll wait if there are any other questions. If not, I'll wrap up. Someone has asked in the YouTube chat, can you please share the book you are using for reference? If you head over to the link that I mentioned, it's called Deep Learning with PyTorch. It's one of the best books on the topic apart from the Fast A book. It's by Manning Publication. And if you read closely, Thomas Freeman is one of the co-authors that joined the first session. So I am assuming you're new to this. Check out the first session for a Q&A with the author. He was very kind enough to join us. I think we're out of questions and we're out of time. So for that reason, I'd like to wrap up. Thank you everyone for joining again. Next week, we'll look at convolutional neural networks, and that'll mark the end of part 1 of the book, post which we'll start building our complete end-to-end project. Not our, I mean, the authors have done it for us, but we'll just look at it. Thanks for joining. I'll see you next week. Please try doing the homework if you can.